Hey everyone. So we left off having calculated the Euclidean and Manhattan distance for three pairwise observations, right? Between individuals 1 and 2, between individuals 1 and 3, and between individuals 2 and 3. And we have information for each of these three people on two variables: the number of product views they had for products made by Patagonia and the number of they had for products made by North Face. Well, it's probably not hard to imagine that if we're trying to do customer segmentation, we really have more than three people we're looking at. And we have more than three variables. When we have large data sets, R will calculate all the similarity measures for us. And so we're not going to be having to do that, but what we are going to be needing to do is to understand. We need to understand what the similarity measures are, which we've gotten this with Manhattan and Euclidean distance. But we've got one more problem that I want to walk you through solving so that when we tell R that we need to standardize or normalize the data, you're understanding what that is and why we do it. So these three people, customers 1, 2, and 3, and how many views of Patagonia, how many views of North Face, they're actually part of something a lot larger. Here they are again, observations 1, 2, and 3, and we've got the number of screen views for Patagonia, the number of screen views for North Face, but we also have their age, their income, how much they spent with us last year, the number of purchases they made last year, and their average purchase amount. And now if I want to segment them, I'm not going to calculate a pairwise observation and compare each of them. R is going to do that. But I want to draw your attention to a problem and show you how we solve it. And the problem is this, is that if we look at the number of views customers have, of these two brands, I can see a range, somewhere between 19 is the max for Patagonia. And what do I have? A 1. North Face, I've got somebody who viewed it 0 times and up to 15, 16 times. Very small numbers. Less than age, right? Which seems to range between, 18 and 71. I might not be getting those exactly right. But on a whole other scale is income. And if we take these numbers and use them to calculate this formula, the difference between individual 1 and individual 2 with regard to Patagonia views, between 1 and individual 2 with regard to North Face views, with regard to their age, in regard to their income. The difference is between income. Here we've got a difference between income and income, like what is that? I'm just going to call it 30,000. That difference of 30,000 is going to dwarf the difference of 1 for Patagonia views. And income is one variable, but we don't want to let it dominate. Otherwise, we'll just be looking at how similar people are with regard to income. I'm going to show you this. You can follow along if you want, but the purpose is really the next step, which is why we need to standardize. So I'm going to come along here and I'm going to just first calculate the squared distances. And I'll do the absolute distances too. And that will leave us in the end with having a Euclidean distance and a Manhattan distance. To do a lot of these, I like to just copy the variable names over. I'm going to have to zoom out a little bit. I swapped screens. And here, because I don't want to make this really large, I don't want to have to thicken it up, make it taller. I'm just going to, x1 to x7. It's the same thing. Okay. So if I want to do, I know why I had that, just kidding. Formatting mania happening over here. Let's make observations smaller. I want you to be able to see everything without zooming so far out. Okay. All right, here, so we have to do the pairwise observations, remember? So between 1 and 2, between 2 and 3, and between 3 and, I should think before I type, between 1 and 3, and between 2 and 3. I just want to make sure that that's the order I went in before. 1 and 2, 1 and 3, 2 and 3. 1 and 2, 1 and 3, 2 and 3. Okay. So I'm going to start with the squared distances and the absolute distances, and I'm going to sort of follow this formula. I'm going to go a little more quickly this time. So between 1 and 2, Patagonia views, 7 minus 6 squared. Between 1 and 3, 7 minus 2 squared. And between 2 and 3, 6 minus 2 squared. Once I'm certain of all these formulas, right, that compares 1 and 2. This one compares 1 and 3. This one compares 2 and 3. I can drag this over, and then I can just calculate the square root of the sum and this tells me that observations 1 and 3 are the least different because they have the smallest Euclidean distance. Well, here's the rub, my friends, is that observations 1 and 2, they have the most similar viewing behaviors. You can see that the distance, the squared differences is low, right? They're more similar in age, 50 and 56, than either of them are to observation 3, who's 32. I'm going to skip income for a second. I'm going to look at what they spent last year, 500 and 549. They are more similar with each other than either of them are to person 3, who spent $1,200 last year. And also 1 and 2, they each made more purchases and had lower dollars per purchase. Person 3 had one large purchase. So 1 and 2 appear more similar, but where they're different is on income. The difference between 111,000 and 87,000 yields them a squared income difference of whatever this gargantuan number is. And because 1 and 3 are more similar in income, they have a closer squared distance, and that dominates when it comes to calculating Euclidean distance, and it makes 1 and 3 seem more similar when they're not. We could do the same thing, and I encourage you to try setting this up with Manhattan distance and calculating those again. But what I want to do is use this video time to show you how to solve it. So what I'm hoping you're seeing is that because the scale of income is large, whatever observations are most similar with regards to income are going to be the ones that seem the most similar in our total measurement, unless we do something about it. Even when another pair of customers are much more similar, they're much closer, they're less different with regard to everything else. So how do we tackle this? What we're going to do to tackle this is duplicate this sheet. You can just put it wherever you want. And rather than calling it raw, we're just going to call it adjusted. And how I'm going to adjust it is to do what's called normalizing the variables. Normalizing and standardizing have a variety of different meanings in different places, but how I'm going to use them here is to say that if I'm going to normalize something, I'm going to turn everything into its z-score, and then I'm going to compare the z-scores, not the raw values. I'm going to get rid of this for a second. And then I'm going to unmerge these cells just to make my life easier. And then here you can see in this row, we've got Patagonia, we've got North Face, right? So can I just come down here and calculate the mean and standard deviation for each of these variables in this column? So what am I doing? I'm going to take each of these variables and replace them with that person's z-score for that variable. What does that mean? The z-score just tells you how far an individual is, measured in standard deviations, from the average value. So how many Patagonia views were there on average? What was the standard deviation? Well, how does this person score compared to average? And then we'll compare people about where they land in the distribution rather than their raw numbers. And that'll help even out the relative impact of things with small scale versus large scale. So the mean for Patagonia views is the average of all the data, all the observations for the variable of Patagonia views. And then the standard deviation, STDEV, I'm going to still use a sample because I believe these are a sample of our customers, not all of our customers. So on average, this sample of customers looked at 10 products by Patagonia with a standard deviation of 6. I can copy these if this makes it a little bit easier. And so I can do this for all of our variables. So and then let's just format these as numbers. So the number of North Face product views on average was 8.69 with a standard deviation of 4.9. With regard to age, our customer's average age is 45 years with a standard deviation of 14. Our customer's average income was about $61,000 with a standard deviation of $36,000. On average, last year, people spent $344 with a standard deviation of $249. That was their annual spending. And on average, our customers made 1.7 purchases per year with a standard deviation of 1.3. And in terms of how much they spent per visit, they averaged $245 with a standard deviation of $216. So where are we going with this? Well, rather than knowing what the actual values are for each of these variables for all of our people, I'm going to make a really big chart and then I'm going to hide some things. I've got 7 variables here. I need to add 7 more columns. Then I'm going to copy the names of the variables. Stick with me here. I'm going to merge these and I'm going to call these normalized values. Right? As opposed to here, what are really my raw values. I'm going to make these larger. And I know we're going to have to kind of scroll a little bit here. So let's just tackle Patagonia first. I'm hiding some rows so I can see that person number 1 had 7 product views for Patagonia. That's less than the average. So they viewed fewer Patagonia pages than average. They viewed fewer North Face pages than average. They are older than average. I hid the rest of them. You'll get the idea when we go there. So our z-score says, all right, if person 1 saw 7 product views, how many standard deviations are they away from average? So if they viewed 7 product pages and the average was 10.57, They viewed 3.52 pages less than average. I'm just going to change this to number. So they viewed fewer Patagonia views, had fewer Patagonia product views than average. I'm going to place this in parentheses, and I'm going to divide it now by the standard deviation. And so person one was about a half a standard deviation below average with regard to the number of pages or Patagonia products that they viewed. I want a value like this for every observation, for every variable in this data set. R will do it very quickly, but if I'm going to do it on Excel, what I want to do is always reference the variable in my row. So I want to reference Patagonia, and when I drag this over, I want it to stay referencing in row 3, but I want to divide it by Patagonia's mean and Patagonia's standard deviation. So to always be subtracting Patagonia's mean from the Patagonia's views, and then to be able to drag down, I want to put a $sign so that what I reference stays in this cell but lets me drag it across. So I want a $sign in front of the 15, but not in front of the R. And I'm just going to place it there. Same thing when I want to divide by the standard deviation. I don't want it to move out of row 16. So my formula, oh, it doesn't like that because I've had too many things. It doesn't really help, does it? Well, there you can see. If your cells are in the same places that mine are, that's your formula. Now I'm going to unhide these cells. I really am going to unhide all of those cells. And now I have what's going to be my raw values here. And then next to this is going to be my normalized values. So person number 1 is just over a half a standard deviation below average on Patagonia views. And if I drag this to the right, I can see that person number 2 is about 3/4 of a standard deviation below average with regard to the number of North Face pages they viewed. They viewed 5, the average was 8.69, so they're about 3.69 views below average, and if I divide that by the standard deviation of 4.9, they're about 3/4 of a standard deviation below average for North Face views. They're slightly older than average, excuse the noise. There's my age, they're 56, average age is 45, so they're 0.7 standard deviations above average, with an income of $111,000 compared to our average income of $61,000. They're 1.35 standard deviations above average with regard to income. Having spent $500 last year, they're over our average spending of $344. They're 0.63 standard deviations above the average. They made 4 purchases per year, which makes them 1.7 standard deviations above average with regard to the number of purchases, but with an average purchase amount of $125, they are below average by about a half a standard deviation below what the average customers or the average purchase amount is. Now that I've got that, I can send this all the way down. And now I've got my raw values and my normalized values. If you're feeling at all like you need to walk through that a little bit more, you could click on any value. So for person 6, they viewed Patagonia 17 pages. The average was 10. So they're 7 above average. That's going to be a little bit more than 1 standard deviation above average. And their z-score is 1.08. All right. Now, what we're going to do is calculate the Euclidean distance and the Manhattan distance based on the normalized values rather than on the actual values. And now the scale for income is the same as the scale for all the other values. Every value now is going to be centered around 0. 0 meaning someone's exactly equal to average. Positive numbers mean above average. Negative numbers mean below average. And very few people will have a score for anything above 3, because that's based on the normal distribution where we're going to get the vast majority. Person 3, you can see they have a z-score of 4.45, meaning they spent 4 standard deviations greater than average on that one purchase, their average purchase amount, because they only made 1 large purchase from us, so that's why their z-score is so large. Okay, squared distances. We're going to do the same thing between 1 and 2. Concrete day here. So the distance between person 1 and person 2 with regard to Patagonia purchases is 0.03 between person 1 and 3. .69, and between person 2 and 3, .44. So we can see with regard to how many Patagonia pages were viewed, person 1 and 2 are the most similar. I can calculate this for everything, each one, but I'm just going to drag it over. And then I had borrowed my Euclidean distance summary from the other page. And now we can see that the Euclidean distance for person 1 and 2 is much smaller, meaning they're much more similar than person 1 and 3 and 2 and 3 are. So by standardizing or normalizing in this case, the data by turning it into z-scores, we've been able to bypass the problem of some variables being a very large scale and other variables being a very small scale. So we can, when we compare it to our raw data that found observations 1 and 3 to be the most similar simply because the scale of that income, we can see when we normalize the data that we don't have that problem. 1 and 2, again, seem to be the most similar. If we take this for Manhattan distances, we take the absolute value of the distance between person 1 and person 2. Then we take the absolute value of the distance between person 1 and person 3. And then the absolute value of the distance between person 2 and person 3. We can drag this over. So with regard to purchase amount, it's referencing person 1 and 2. It's referencing purchase amount for person 1 and 3, and referencing purchase amount for person 2 and 3. And we can see that the absolute difference between the purchase amount z-scores for person 1 and 2 are much closer. So to get the Manhattan distance, we add up those absolute differences. And we see again that, like with the Euclidean distance, the Manhattan distance yields the same result, which is that observations 1 and 2 are the most similar in this data set. And when we were looking at raw data, we didn't see that because the income value was dominating. So it reflects what we see in the raw data, which is that with regard to viewing behavior, 1 and 2 are more similar than either of them is to 3. When it comes to age, they're more similar with each other than either of them is to 3. With income, 1 and 3 have closer values. With last year's spending, 1 and 2 are more similar with each other than they are with 3. Same thing with last year purchases, same thing with average purchase amount. So on most of the variables, 1 and 2 are more similar, but because income has the largest scale, if we don't normalize or standardize the values, we're going to find that 1 and 3 are going to look the most similar because they're the most similar on one variable, and that one variable has the biggest scale. So that is why we need to normalize or standardize. Once we get into applying this in R to try to figure out customer segments or looking at groups of products that are similar, vehicles or types of candy or whatever it is that we're going to take on, we're going to ask R to normalize or standardize. And we're going to have to specify to R whether we want a Euclidean distance measure or whether we want a Manhattan distance measure. R will do that for us, and our job will be to interpret. So what I want you to have at this point is an understanding of why we normalize or standardize and the difference between those two measures. All right, peeps, thanks very much, and I will talk to you soon.